These videos are offered on a pay-what-you-like basis. You can pay for the use of the videos at my website. There's a link to my website in the info box. The address is www.freelance-teacher.com/videos.htm. Or you can just use the link in the info box. Thank you. The next concept I want to go over with you then, we'll just get started on what we'll talk about tomorrow. What's the symbol for heat?
Q.
And what's the unit that we've usually been using for heat?
Degrees Celsius.
Like this?
Yeah.
Think again?
I'm saying joules.
Right. What's degrees Celsius the unit for?
Temperature.
Right. We talked about how it's easy to confuse heat and temperature, so we want to be careful not to do that. Now, another concept we've gone over is specific heat. What would be a good symbol for that?
Q.
Like this?
Yeah.
I think you might be misremembering that. Try again. What's the symbol for specific heat?
Specific heat is that was C.
Capital or lowercase?
Capital C.
Actually, I think you're misremembering that. Specific heat is lowercase c. That's what we've been using in all the problems that we've been doing so far. Like in the Q equals mc delta T. Maybe I should have made that clear. We've been using a lowercase c. All right, and do you remember, or can you look up what are typical units for specific heat?
Joules per gram, degrees Celsius, and kilojoules per gram degrees Celsius. It could also be kilojoules per kilogram degrees Celsius.
All right, those are good answers. So those are a lot of different possibilities, but the first answer you gave is the one we usually use in chemistry. That's good, although we've seen a couple others. All right, good. So now we're going to go on to, so for example, what's the specific heat of liquid water?
4.184.
How would you interpret that number? What does that tell you about liquid water?
That for every gram of water takes 4.184 joules to raise it 1 degree Celsius.
That's right. The C for water is this. You can put ones on the bottom to help you interpret that. Now, how about specific heat capacity? Do you know what the symbol is for that?
Specific heat capacity would be that would also be Q. Well, actually, no, that would be capital C.
Now, that was kind of a trick question. We did talk about this, but that was a couple sessions ago. Specific heat capacity means the same thing as specific heat.
So it would be Q.
Well, no, think again. Specific heat capacity means the same thing as specific heat. So what's the right symbol for it?
Lowercase c.
Lowercase c, not Q. We don't want to confuse heat with these other things. All of these have the word heat in them, so people tend to confuse them. So specific heat capacity is identical to specific heat. They're the same thing. So unfortunately, chemists use two words here to mean the same thing. These are identical concepts. Now we're going to learn a new concept, which is called the heat capacity. Notice that the key word that's missing here is specific. If they say heat capacity, they mean capital C. And the units for heat capacity are joules per gram. Those are common units, joules per gram. Nope, let me try again. The units are joules per degree Celsius. Let's say that you had, say, 3 grams of liquid water. Or actually, let me put that aside. So let's suppose that something has a heat capacity of 8 joules per degree Celsius. How do you think you would interpret that? If the heat capacity is 8 joules per degree Celsius, how do you think you would interpret that? What does that tell you about that sample?
For that particular sample, it takes 8 joules to raise that sample's temperature 1 degree Celsius.
Good, so you put the number 1 on the bottom. That was a good explanation. That sample, it would take 8 joules to raise the temperature by 1 degree Celsius. That's a good explanation. Now, let's say that we have 3 grams of liquid water. Can you figure out how would you calculate the heat capacity for that 3-gram sample? How would we find the heat capacity of this 3-gram sample of liquid water if you know that this is the specific heat of liquid water?
Well, you would just take 4.184 and you would divide it by 3.
So tell me what to write down with the units.
.184 joules divided by 3 grams per degree Celsius.
I see. Okay. All right, I see what you're doing. Now, so what you're trying to do is you're trying to stick the grams into this expression. That won't work because remember, the specific heat is not 4 divided by 3. It's 4 divided by 1. Otherwise, you'd have a different specific heat. Now you're trying to put the number 3 here on the bottom, and that would not come out right. Also, notice that would give you the wrong units if you did that. Because if you did that, you would end up with units of joules per gram per degree Celsius, which is not the right units. So we need to start with the specific heat.
So then we would just multiply it by 3 grams. That way the grams cancel.
Yeah.
And then
good.
You will get for a total of 12.5 joules per degree Celsius.
Yeah, let's see. So that would be 4.184 times 3, 12.5 approximately, 12.6 approximately. Now the units cancel nicely, and we get the units we want. So what does that tell us is the general formula for calculating the heat capacity? If you know the specific heat, what do you do to find the heat capacity?
You multiply it by the weight of the substance.
Good, except in science this is not called the weight, it's called the mass. So here's our equation. Capital C equals little c times m. So the heat capacity is little c times m. So notice, if you just have water in general, you have to give the specific heat, which tells you how much energy it takes to raise 1 gram by 1 degree Celsius. But if you have a specific mass of water, you can find the heat capacity of that specific mass in joules per degree Celsius. All right, so this is confusing because all these terms sound similar, but they mean different things. So what does the word specific mean? If you look at these, you can see, would you agree with me, specific means kind of per gram. That's the difference between heat capacity and specific heat capacity. When you say specific, you mean per gram. Do you see why I'm saying that?
Not really.
Well, here's the heat capacity. That's joules per degree Celsius. What changes when we find the specific heat capacity? Well, the thing that changes is that then it changes to joules per degree Celsius per gram as well. So I guess that in science, specific kind of means per gram, at least with these terms. So both of these two things are actually the same thing because they're both specific. So they're both per gram. But when you take out the word specific, you have a new concept. Okay, so I guess tomorrow we'll move on to the bomb calorimetry. And so for that, we're going to need the heat capacity. So these would be good things to review as we're going on to that. Okay. Well, let's start with reviewing the concepts that we finished with yesterday. What's the symbol for heat?
The symbol for heat is Q.
And what are the units we commonly use for heat in this course?
The common units for heat are joules and kilojoules.
Yeah, that's right. You might see some problems that use calories, but I didn't see any of those in the handouts that you sent me. What's the definition of heat?
Heat is it's how much energy, or actually, not how much energy, but how fast the molecules are moving apart. Like when one substance, it's the transfer of energy of a substance that has high energy to a substance of lower energy.
Okay. Now, there was a couple different approaches in what you just said. So try that one more time. What would you say again? What is heat?
It's the energy that is transferred from high temperature to low temperature of a substance.
That is a good answer. Yeah. Heat is energy that's transferred between a high temperature and a low temperature substance. So you ended up with the right definition. That's good. Do you remember what the symbol is for specific heat?
It's lowercase c.
Yeah, lowercase c. That's right. And what units do we usually use for specific heat?
Joules per gram.
Like this?
Yeah.
Now, actually, the units for this concept were joules per gram per degree Celsius. You might have been confusing this with something else we talked about yesterday. So those the earlier units you mentioned were incorrect. We have to use these units. Okay. How about this concept, specific heat capacity? What would be the symbol for this concept?
It would also be lowercase c.
That's right. So what are the units for specific heat capacity?
Joules per gram degree Celsius.
Because it's identical. To the concept of the specific heat. For example, what's the specific heat of liquid water?
It's 4.184 joules per gram per degree Celsius.
How would you interpret that number? What does that tell us?
For every 1 gram of a substance, or in this case liquid water, it takes 4.184 joules to raise the temperature 1 degree Celsius.
Good. So we've seen that when you have compound units, a good technique is to put a number in front of each of the subunits. Well, the only number that we can write down here without changing the value is the number 1. And that gives us a concrete interpretation. Just like you said, if you have 1 gram of water and want to raise its temperature by 1 degree Celsius, it'll take 4.184 joules of energy, of heat. Good. What's the symbol for heat capacity?
That is also capital C.
That is capital C, unlike specific heat or specific heat capacity, which is lowercase c. So I'll have to try to be careful distinguishing between those. I'll try to write a lowercase c in a kind of cursive form and the uppercase c like this. And of course, we also have to try not to confuse this with Celsius. So we have to put the little circle to show degrees Celsius. That's different than this. Okay, good. Do you happen to remember what are the units for heat capacity?
That would be joules per gram.
Let's see. Actually, I think that's incorrect. This actually should be joules per degree Celsius. Do you remember at the end of the last session we were talking about if you compare these concepts, we can kind of figure out what the word specific seems to mean. It seems that specific means per gram. Do you see why we would say specific means per gram? Because all the concepts that have the word specific in them are per gram. Specific heat is joules per degree Celsius per gram. Specific heat capacity is joules per degree Celsius per gram. But when we take out the word specific, now it's just joules per degree Celsius. We lose the per gram. So I guess specific means per gram. Okay. And do you remember last time we got a formula for calculating heat capacity?
Yeah.
Remember what that formula is?
It was...
It's also a formula we could figure out from the units. That's how we figured it out last time.
It was the specific heat capacity, lowercase c, times grams.
Okay, now that's not a full formula, so what would the full equation be?
So capital C is equal to lowercase c times the number of grams.
And what's the name for the number of grams? What concept does that measure?
Mass times the mass.
So here is the formula we came up with. We proved that this formula makes sense because you would have the same units on both sides of this equation. So let's say that we have 5 grams of water. What's the sample's heat capacity? Let's try working that out on paper and tell me what you're writing down.
So capital C is equal to lowercase c times m, where capital C is equal to 4.184 times 5 grams. That is equal to approximately 21 joules per degree Celsius.
Good. I usually advise you not to write down the units when you're plugging into equations, but this time I think it'll be instructive to plug in the units. So what are the units for this number?
Grams.
And what are the units for this number?
Joules per gram per degree Celsius.
So what would happen with the units in this equation?
The grams will cancel out.
And what do you have left?
Joules per degree Celsius.
That's right. So as I was saying, this formula is obvious from the units. If you check the units, you can see this formula makes sense. Okay, so now what does this number 21 tell us? How would we interpret this number 21 in words? What does it tell us?
For water, liquid water, it'll take 21 joules to raise 5 grams of water 1 degree Celsius.
So again, since you have compound units, you wanted to put a number on the bottom. And the only number you can put here without changing it is 1. Good. Now, the key thing that you noticed here is that this is not true for any sample of water. It's only true for this particular sample. So you were saying, for our particular sample of water, it would take 21 joules to raise that particular sample by 1 degree Celsius. Now, notice down here, now this is not, there's no specific reference to mass in the heat capacity. There's no specific reference to mass like there is up here, because the heat capacity is only defined for a specific sample that already has a given mass. So as you're saying, this is telling us that for the sample that we're dealing with in this problem, the 5 gram sample, it would take 21 joules to raise the temperature by 1 degree Celsius. We already know how much heat it would take to raise the temperature of 1 gram by 1 degree Celsius. That would be 4.184. So this tells us to raise this 5 gram sample of water by 1 degree Celsius would take 21 joules. All right, well, so maybe you can see the similarities and differences between heat capacity and specific heat. So does specific heat refer to a type of substance or a specific sample of the substance? Would you talk about the specific heat of a type of substance or a specific sample of the substance?
A specific sample?
Not for specific heat. Then maybe that was a confusing question, but remember that specific heat, the specific heat is just for a type of substance.
Oh, sorry, yeah, for specific heat, it would just, for heat capacity, it would be for a certain amount of a substance.
Yeah, but the heat capacity is for a given sample that has a set mass. Actually, it doesn't have to just be one substance. It could be a mixture of substances, but it would still be for a given sample, which is a mixture of substances. I don't know, maybe that clarifies the difference between how we would use those two concepts. All right, so anyway, I find that people tend to confuse all these ideas. Sometimes people confuse heat and specific heat, or they confuse heat and heat capacity, or specific heat and heat capacity. It's especially confusing because there's two terms that mean the same thing, specific heat and specific heat capacity. It's like it was designed to be confusing. All right, so, well, we'll work on that. So let's see. We're going to be talking a lot about combustion reactions here, so maybe we should review that. Suppose that we are combusting, say, methane. Do you know what's the definition of a combustion reaction? What does combustion mean?
The products are going to be carbon dioxide and water.
Okay, good. That's a good start. So how would you write the equation for the combustion of methane? Try writing down the equation for the combustion of methane.
Well, we have CH4 plus O2 goes to CO2 plus H2O. And we can put a number 1 in front of the CO2. We can put a number 1 in front of the CH4. That balances the carbons. Now we can put a number 2 in front of the water, so now the hydrogens are balanced. We have 4, and then we can put a number 2 in front of the oxygen. That way, 2, that's 4, 1, 1, 4, 4. Yeah, and then we can put a number 2 in front of the oxygen, so everything is balanced.
Good. That was a good approach. Okay, yes. Now, when you defined combustion a second ago, you said that combustion reactions produce carbon dioxide and water. That's true when you're combusting hydrocarbons. When you're combusting a hydrocarbon, the carbons turn into carbon dioxide and the hydrogens go into water. That doesn't quite define combustion. I could say a combustion reaction is when you react something with oxygen. That's the That's the definition. A combustion reaction is when you react something with oxygen. Why is that called combustion? You know that combustion that means burning, right? Well, the point is, these reactions, when you react something with oxygen, those are generally highly exothermic. They release a lot of heat. So typically you'll get a kind of a burning when you're doing this reaction. That's why reacting something with oxygen is called combustion, because it's generally exothermic enough that you release so much heat that it basically looks like it's burning. Okay, good. Now, remember I was just saying that combustion reactions are exothermic. This is going to release a lot of heat. How can you measure how much heat is being released? Well, the way this is done is what's called calorimetry. And what you do is you have some type of container in which you are carrying out the reaction. Some type of container in which we're going to carry out the reaction. And that might be in another container that's full of water. So when the reaction occurs, if it's exothermic, it's going to be releasing heat to the water. What's going to happen to the water when the heat goes into it?
It's going to absorb it.
That's right. So what else will happen? How can you see that it's absorbing the heat?
The temperature of the water will increase.
Yeah, so the temperature of the water will increase. In fact, the temperature of this entire apparatus will increase. The temperature of the entire apparatus, the entire calorimeter, will increase. But we've already learned how to figure out how much heat it takes to raise the temperature a certain amount. So we can measure in the lab how much the temperature went up, and that will tell us how much heat was released. So this is a basic picture of how a calorimeter works. One type of calorimeter is what's called a bomb calorimeter. It's not as exciting as it sounds. So I think bomb here is just a fancy word for a sealed vessel that maintains a constant volume. So basically, a bomb calorimeter is just a container that maintains a constant volume and is containing the reaction. Okay. Moment. Ow. Remember when we were talking about specific heat, we had an equation that allowed us to use the specific heat to find the amount of heat. Do you remember what's the equation that links specific heat and heat?
Could you repeat that?
What's the equation that links the specific heat and the heat?
So that would mean Q total is equal to the summation of the Q's.
That's a true equation, but notice that that doesn't link specific heat and heat because it doesn't include little c. We need an equation that includes both little c and Q.
Oh, so that would mean Q is equal to MC delta T.
What does M stand for?
It's the mass.
The mass of what? It's the mass of the thing that's changing temperature. And what does Q stand for?
That's the heat.
The heat transfer. The heat transfer for who? The heat transfer for the thing that's changing temperature. Q is the heat transfer for the thing that's changing temperature. So now in the examples we're doing, Q would be the heat transfer for the calorimeter apparatus. Q would be the heat transfer for the calorimeter apparatus. Now, most of the problems we're going to do now are not going to involve specific heat. They're going to involve heat capacity, capital C. Can you think, how could you rewrite this equation so that it involves capital C and not lowercase c? How can we rewrite this equation so it has a capital C in it and not a lowercase c?
Well, I guess substitute the lowercase c for capital C.
So what would be the new equation?
Q equals M capital C delta T.
So it sounds like you're doing this substitution. You're saying that capital C is identical to little c, and you're substituting in. But this is not a true equation, so that was incorrect. What we need is a true equation that links capital C and lowercase c before we can substitute them in.
So then, we know that capital C equals M lowercase c.
That's right. So how could we rewrite this equation so that it has capital C rather than lowercase c?
So
Are you working on that?
yeah.
Okay. It shouldn't be a very complicated procedure. If you're doing something very complicated, you're probably on the wrong track.
I'm not quite sure.
Okay. Now, like I said, this actually shouldn't be that complicated. Here's an equation that has little c. Here's the link between capital C and little c. I don't know, try again. How could we rewrite this equation so that it's in terms of capital C rather than lowercase c? Any ideas?
So in terms of capital C instead of lowercase c, Q is equal to capital C delta T.
How did you come up with that?
If heat capacity is equal to N times the specific heat, and Q is equal to M times the specific heat times delta T, then we can just substitute in the heat capacity, capital C, and for M the mass times the specific heat.
Okay, now you got it. That's right. That's correct. Heat capacity and specific heat capacity are closely related, so these equations are closely related. So now in this calorimetry section, we're mainly going to be using this equation because the problems are usually going to give us the heat capacity, not the specific heat. Now, what does the capital C now stand for? Capital C would stand for the heat capacity of the calorimeter apparatus. This would be the heat capacity of the calorimeter apparatus, and delta T would be the change in temperature of the calorimeter. So then what would Q stand for?
Could you repeat that?
If capital C is the heat capacity of the calorimeter and delta T is the change in temperature of the calorimeter, what would Q stand for?
That would be the heat transfer of the calorimeter.
Yeah, that would be the heat transfer to the calorimeter. But there's a complication. Remember that what we really want to figure out is the heat transfer from the reaction. What we're really interested in is the heat transfer from the reaction. Well, what do you think is the relationship between those? Suppose that the calorimeter has absorbed, if the calorimeter has absorbed, say, 8 kilojoules. If the calorimeter has absorbed 8 kilojoules, would the Q for the calorimeter be positive or negative? If the calorimeter has absorbed 8 kilojoules, would the Q for the calorimeter be positive or negative?
The Q would be positive.
But then what would be the Q for the reaction?
The Q for the reaction would then be negative, since if the calorimeter is absorbing heat, then that means that the reaction should be releasing the same amount of heat. Therefore, it would be negative 8 kilojoules.
That's a good answer. That's right. And this is the number we really care about, because the whole purpose of the calorimeter is to measure how much heat is being released by the reaction. So generally, we're going to be applying this method to exothermic reactions. Exothermic reactions that release heat, so we can see the change in the temperature. So notice, what's generally the relationship between Q for the reaction and Q for the calorimeter? What's the relationship in general between Q for the reaction and Q for the calorimeter?
Well, that means that the Q total will equal the Q for the calorimeter plus Q of the reaction.
Well, that's true. That's just really the definition of Q total. We can get a more specific relationship that you already used to get these two numbers. In order to get these two numbers, what were you assuming was the relationship between the Q for the calorimeter and the Q for the reaction? Let me give you another example. If the Q for the calorimeter was positive 7 kilojoules, what would be the Q for the reaction?
Negative 7 kilojoules.
Because what this means is that the calorimeter absorbed 7 kilojoules of heat. Where did that come from? It must have come from the reaction releasing 7 kilojoules. So in general, what's the equation that relates Q for the calorimeter and Q for the reaction?
Relationship.
If you know Q for the calorimeter, how can you figure out the Q for the reaction?
Oh, so then it would just be the total Q minus Q for the calorimeter.
Let's see. Actually, it's actually even simpler than that. We don't even need to think about the concept of the total Q here. Let me give you another example. I'm going for a pretty simple idea, but I want to make sure this is something that's apparent to you. Suppose that Q for the calorimeter is positive 6 kilojoules. That means the calorimeter absorbed 6 kilojoules of heat. How would you figure out the Q for the reaction?
Well, it's the same, so it would just be negative.
So it's not exactly the same, is it?
Not really, no.
So if you know Q for the calorimeter, how do you figure out Q for the reaction? What did you just do?
Could you say that again?
Yeah, if you know Q for the calorimeter, how do you figure out Q for the reaction? What did you just do to figure out the Q for the reaction from the Q for the calorimeter?
You um maybe I'm just overcomplicating it, but
Yeah, okay. I guess maybe that sounds like a weird question to you. Isn't what you did is that to figure out the Q for the reaction, you took the negative of the Q for the calorimeter?
yeah.
Okay, so that's what I was going for. I'm not quite sure what was confusing you about that.
Okay.
Yeah. So I guess you weren't quite understanding what the question was there. But if you know the Q for the calorimeter, how do you figure out the Q for the reaction?
I guess you would just have to take the Q for the reaction, although you already know that it's going to be positive for the calorimeter, so therefore any heat from the given off by the reaction is going to be the same number, except it'll be exothermic, so just negative.
That's right. That's right. It sounds like you're still maybe overthinking a little bit. So what I'm going for is, if you know the Q for the calorimeter, you find the Q for the Q for the reaction is the negative of that.
Okay.
All right. I guess the problem that you're having is that you're doing the specific problems correctly, but in science, what we have to do is find general equations or general relationships. After you've learned how to do something with specific numbers, you need to ask yourself for what's a general rule or a general formula for moving between those. So let's try again. What's the relationship between the Q for the calorimeter and the Q for the reaction? What's the general relationship between the Q for the calorimeter and the Q for the reaction? How would you summarize what we were just talking about?
Well, if the Q for the calorimeter is positive, then Q for the reaction is just a negative number of that.
That's right. So what would be an equation that links Q for the calorimeter and Q for the reaction?
I guess Q total is equal to Q of the calorimeter plus Q of the reaction.
That's a true equation, but that's not as specific as we could use. We don't need that idea of Q total here. That's not really how you were going. You didn't use the idea of Q total to go from one to the other. Let's try again. This is an important skill to be able to get a general equation from a specific rule. So I'm going to ask you again. What's a general equation that links Q for a calorimeter and Q for a reaction if you were with no other variables? If you were going to write an equation that has just those two variables, Q for the calorimeter and Q for the reaction, what would be an equation that you could write about those two variables? And
I guess no Q for the calorimeter is equal to -1 times Q of the reaction.
Okay, yeah, that's what I was going for. Okay, maybe I should have explained that more clearly, but it's important to start getting into the habit of writing a general equation that summarizes what you're doing. It's not good enough just to be able to do specific problems. We also need to be able to write a general equation that summarizes that relationship. So we can say, that's really what I was going for with all those questions I was asking you. Notice that you don't need the idea of Q total there. We just have Q calorimeter equals the negative of the Q of the reaction. Where does that come from? Well, we know that if you have Q for the calorimeter plus Q for the reaction, that does equal Q total. But for these problems, what is Q total going to be? For these problems, Q total is 0, because as usual with the two-substance problem, we're assuming that this is insulated from the environment. We're assuming that the calorimeter and the reaction are insulated from the environment so that the total heat exchange has to add up to 0, because there's no one else for them to absorb or release heat to. And then if you solve this, you would get Q for the calorimeter is the negative of the Q of the reaction. All right. So when I ask a question like, what's the relationship between two variables, what a scientist means by that is write an equation about those two variables. when you're asked what's the relationship between two variables, what a chemist means by that is write an equation about those two variables. And when possible, you want to have as few other variables as you can. So that's the relationship. Now, all right, that was a little bit of a detour. Coming back down to here, remember we saw this was an equation for finding the heat from a calorimeter. But what we really care about is the heat from the reaction. We want to know what's the heat released by the reaction. Well, how could we adapt this equation so that this equation is about the heat for the reaction rather than the heat for the calorimeter? How could I rewrite this equation so that it's about the heat of the reaction and not the heat of the calorimeter?
Could you repeat that?
This equation is about the heat of the transfer to the calorimeter. What we care about is the heat from the reaction. How could we rewrite this equation so it's about the heat of the reaction? We want to use our previous work.
Q calorimeter is equal to negative Q of the reaction.
Now that's a true equation, but that doesn't involve these other variables here. What I want is an equation that does not have Q for the calorimeter, but does have Q for the reaction, and also has capital C and delta T. So what's an equation that we could write about capital C, delta T, and Q for the reaction? We need an equation about these four variables. I'm sorry, these three variables. So I'd like you to take this equation, which has Q for the calorimeter, and I'd like you to rewrite it as an equation that's about these three variables and that does not include Q for the calorimeter.
Well then Q of the reaction is equal to the heat capacity of the reaction times delta T.
Like this?
Yes.
So it sounds like you're saying that this equation is almost identical to this one. Basically, you're just replacing these. So what you did here is you're saying that Q for the reaction is the exact same thing as Q for the calorimeter, because you wrote the equations exactly the same. So is that true? Is Q for the reaction exactly the same as Q for the calorimeter?
Oh, it actually should be a negative capital C delta T.
That's right. This is the point of this work that we did up here. The Q for the reaction is the negative of the Q for the calorimeter. So if you were going to substitute in, you're not going to substitute in Q reaction for Q calorimeter, you're going to substitute in the negative of that. I think that once we start doing problems, this will probably be clear to you how to use this. But it's also a real important skill in chemistry to be able to think abstractly in terms of equations. It looks like we're having a lot of trouble with that here, so it would be good to just go back and think about these things again. I think at first you're probably maybe not understanding what I mean by the questions. So when I'm asking something like, what's the equation that relates Q calorimeter and Q reaction, I mean we want an equation like this with those two variables. Or then I asked you, how could we rewrite this equation so that it's in terms of Q reaction? Well, what we need to do then is substitute out this variable and replace it with Q reaction. But we can't just erase one symbol and replace it with the other symbol. We have to do it so that the equation is still true. So we have to remember that Q reaction is the negative of Q calorimeter. So that's an important skill. So it would be good to go back and review all those little steps that we just went through so that we can see more clearly kind of what I was going for there. Okay, so now this is the equation that we're going to be trying to use to solve problems. We had some trouble with that, but what I was trying to convince you is that once you understand these steps, this equation should be kind of obvious. It looked like it wasn't obvious to us, but once you're understanding the steps, this should be pretty obvious. This equation tells you how much heat is being absorbed or is being transferred to the calorimeter, and that's just the negative of the heat that's coming from the reaction, or it's the negative of the heat transfer for the reaction. Let's see. Okay, let's start with this. I actually erased part of the problems. I wanted to start with an easier problem. How would you try this problem?
0.6 grams of N2H4 is combusted. Heat of combustion is N2H4. Is 619 kilojoules per mole. Find the heat released. Well, they're trying to find the heat released, and it's a one sample problem, so Q is equal to MC. Well, we don't know the initial and final temperatures, but well, they're looking for Q. We know the mass, the heat of combustion. Well, that isn't really a specific heat. And then we don't know any temperatures. But I guess the heat of combustion would be a reaction. So Q of the reaction is equal to negative C heat capacity times delta T. Well, actually, wouldn't it just be negative 619 kilojoules per mole?
So what would be one technique I think we've seen in an earlier session? Remember, you need to start by asking what the question is asking for. And sometimes the right way to think about that is to focus on the units. What would be good units for our answer?
Joules or kilojoules?
Good. So did the answer you just gave me match those units? You were just taking a guess as to the answer. What was your answer?
I said it was negative 619 kilojoules.
Okay. Now, where did you get that from?
Well, at first I thought it was looking for Q, and then I was thinking maybe we'd have to use Q of the reaction is equal to negative C delta T, but we don't have the heat capacity, nor do we have a change in temperature.
True. Good point.
And since it says the heat of combustion is 619 kilojoules, since it's releasing
Now,
heat, then I figured that would just be the negative number of that, since it's a reaction.
Yeah, what does it say the heat of combustion is?
The heat of combustion of N2H4 is 619 kilojoules per mole.
Okay, good. So what would be your answer?
Oh, it'd just be 619 kilojoules per mole.
Now, are those the units that we wanted?
Yeah.
I would say no. What's the difference between the units that you're answering with and the units that we wanted?
Oh, well, this is kilojoules per mole, so then we'd have to get rid of the moles. So 619 kilojoules per mole. N2H4 is It's 32 grams per mole, so multiply that by 32 grams per 1 mole. Actually, no. Divide that number. 1 mole divided by 32 grams. So then 619 kilojoules divided by 32. We get 19.34 kilojoules per gram, but we want just kilojoules, so well, I think my first step is right, where I took 619 and I divided it by 32 grams to per 1 mole to cancel the moles of N2H4. And then I get 19 kilojoules per gram. But we still don't end up with kilojoules. Okay. Oh, but then we have 0.6 grams. And now times that by 0.6. And that'll give us 11.6. So that's 12 kilojoules.
Okay. So it sounds like this is the calculation that you did?
Yeah.
And what was your answer?
11.6 kilojoules, sorry.
Okay, yeah. All right, so this is another important skill. This is something we've seen in a bunch of previous examples as well. I don't think we've ever done a problem just like this, but we've used unit analysis before. It's important to be able to take a new problem and use the units to solve it. So here's the way that you can convert from these numbers to the units that we want. I think there might be a way to make this a little bit more intuitive, although I think you came up with the right answer. What does this number, how would you interpret this number, 619 kilojoules per mole? What does that tell us?
For every, Well, if there was like a degree Celsius, then I would say that for every 1 mole of N2H4, you would have, it takes 619 kilojoules to raise it 1 degree Celsius, so...
Okay, but we don't have the degrees Celsius, so we have to interpret it in terms of its actual units. Remember, what's the name of this concept?
Specific heat.
Well, no, go back and reread the problem. What did the problem call this?
Oh, heat of combustion, so it takes that much energy to combust 1 mole of N2H4.
Good, except... is this the heat that's required for the combustion or the heat that's released?
It's required.
Well, is combustion exothermic or endothermic?
It's exothermic.
So it doesn't make sense to say this is the heat that's required. The heat of combustion refers to heat that's released. You might have thought that it was required because this was a positive number, but it's just a convention that we use a positive number for heat of combustion. Because it's assumed that we know that combustion is exothermic and it's releasing heat. So say again, how would you interpret this number?
For every mole of N2H4, it'll release 619 kilojoules per mole. So
it'll release it when?
I'm sorry?
When would it release that energy? It doesn't release that energy just because it's sitting around. When would it release that energy?
It'll release it when it's combusted.
That's right. So this means if we combust 1 mole of N2H4, we'll release 619 kilojoules of energy. So how much energy would we release if we combusted 2 moles? How would you calculate that?
Could you say that again?
How would you figure out how much energy would be released if you combusted 2 moles?
Just take 619 and multiply it by 2 moles.
Yeah, or how would you figure out how much energy would be released if you combusted 3 moles?
Take 619 and multiply it by 3 moles.
Okay, good. So notice that's why there's a difference between the actual heat released and the heat of combustion. At first you were saying that the heat released was the heat of combustion, but that would only be true if we were just combusting 1 mole. So if we're combusting a different amount, we need to do a calculation to find the heat that's released. Now, in this case, we don't know how many moles are being combusted. How could we figure out how many moles are being combusted? How could we figure out how many moles are being combusted in this problem?
In which case?
In this problem, how can we figure out how many moles of N2H4 are being combusted?
Oh, we just take the 0.6 grams and then multiply that by 32, or I'm sorry, divide that by 32 grams to get the moles.
How do I write that as a unit conversion?
To put 32 grams on the bottom and then 1 mole on the top.
So this is how many moles of hydrazine we're combusting. And how could we use that to figure out the heat then that's released in the reaction? How can we figure out how much heat is released when we combust this many moles? This is how much of the N2H4 we're combusting. How can we figure out how much heat is released when we combust this?
Well, since we know that's how many moles of N2H4 combusted, we can take 619 kilojoules per 1 mole and then multiply that by 0.1875 moles of N2H4. And that'll give us 116 kilojoules.
Whoa, what happened? We didn't get the same answer as before. Let's see. Did I make a mistake here? 619.
Oh, it's actually 0.01875 moles.
You're right, I wrote this down incorrectly.
And we get 11.6 kilojoules.
Which is the same answer that you got when you used your method. So you eventually came up with a good method to do this by using the units. I usually recommend doing unit conversions in 1 step, but this I think makes more sense if you do it in 2 steps. So I would suggest doing these in 2 steps. So the point here is the heat of combustion tells us how much energy is released if we combust 1 mole. So then the logical thing to do first is to figure out how many moles we have. Logically, first we should figure out how many moles we have, and then we can figure out how much heat was actually released. So I would suggest doing the problem like this. Okay, but one thing I want to really emphasize is, with practice, you should be able to figure out new problems like this, even if you've never seen them before, just by analyzing the units. By analyzing the units, we should be able to figure out how to do a new type of problem. I might have faked you out here because I moved to concepts that are a little bit different than we were talking about before. We're not using these equations just yet. We're not using these equations just yet. We're going over some other preparatory material. What's the name of this concept? What is this concept? What's the name of this concept? Are you there?
That is heat of combustion.
I think at first you were confusing that with the heat capacity, but notice those are different units. Heat capacity is joules or kilojoules per degree Celsius. Heat of combustion is joules or kilojoules per mole. So we have a lot of different concepts that are easy to start getting confused with each other. It's important to try to avoid confusing all those. Okay, let's try this problem.
Heat of combustion of octane is 5,438 kilojoules per mole. What is the heat released when 500 grams of octane is combusted? So we can take 500 grams octane, and we can divide it by the molar mass, so 1 mole over 114 grams. That'll give us 4.3860 moles of octane combusted. Now we can take 5,438 kilojoules per mole and then multiply that by 4.3860 moles. And I get 23,851 kilojoules.
What was your answer again? What was your answer?
23,851 kilojoules.
Okay, I got 23,872. I guess it makes a big difference how you round off here. I think we were just rounding off differently. Did I do this correctly? 5438 times 4.39. All right, so it's somewhere in the 23,000s anyway, depending on how you round off. This is what I got. Okay, so oh, yeah, if I just use the full number, I get the same thing as you. Okay, good. Good. All right, so these problems are a lot easier once you've seen it done once. But remember, if you see a new problem, you should be able to figure out how to do it. The way we figured this out, remember, was by focusing on the units we wanted for our answer. And we had to ask, how could we manipulate the units that we were given into the units for our answer? That's a common skill in chemistry. Okay, so now this is a follow-on. I guess this would be part B for the problem we were just doing. Think about how would you do part B.
This reaction occurred in calorimeter with heat capacity 6 kilojoules per degree Celsius and initial temperature 25 degrees. What is the final temperature? Well, we know that we're looking for TF, final temperature, and Q of the calorimeter is equal to capital C times delta T. And capital C in this case is actually in joules per degree Celsius, so 6 times 1,000 joules is equal to 6,000. So Q of the calorie is equal to 6,000 joules per degree Celsius times TF minus TI, which is 25. Now we can distribute this number. That is equal to 6,000 TF minus 150,000. So add 150,000 to both sides. That is equal to 6,000 TF divided by 6,000.
All right, let me make sure you're on the right track. What's the equation you have written down now?
I have 150,000 is equal to 6,000 TF.
Okay, let's review those steps. What was the first equation you wrote down?
Q is equal to Q of the calorimeter is equal to C delta T.
Good. And then what was the next equation you wrote down?
Q of the calorimeter is equal to 6,000 times TF minus 25.
Excellent. Then what did you write down?
Q of the calorie is equal to 6,000 TF minus 150,000.
Sounds good so far. All right. Now what's the next equation?
Now I added 150,000 to both sides, and you would just divide by 6,000 to get the final temperature.
Well, let's not forget to write down the equation. So what's the new equation you get when you add 150,000 to both sides?
150,000 is equal to 6,000 TF.
Now it looks like there was a mistake there because you lost this variable. It sounds like what you should really have is Q calorimeter plus 150,000 on the left-hand side, right?
Yeah.
All right, so that was maybe wishful thinking. We can't just ignore this variable. Or maybe you were kind of assuming that this is 0, but there's no reason to assume that's 0. We need to plug in a number for this.
So then Q of the calorimeter is this going to be You know the heat capacity, and we figured out the heat of combustion of octane. So I guess we'd have to take 13,851, or sorry, 23,851 times 1,000. And that'll give us joules. So that'll be our Q of the calorimeter, excuse me.
Good.
23851,000 plus 150,000. So plus 150,000. And that's equal to 24001,000. It's equal to 6,000 TF. Divide that by 6,000. And the final temperature I get is equal to 4,000 degrees Celsius.
That seems pretty high. I must not have set up this problem very well. All right, so yeah, what happened? How did I go so wrong here? Heat of combustion is... Okay, so the problem just turned out not to be very realistic. If you're actually combusting this much octane, octane releases a lot of energy when you combust it. It's like gasoline. So if we were actually combusting this much methane, you would really be reaching a really high temperature. So this is not realistic because the water would start to evaporate way before this. So the numbers that I used didn't really work out very well. I was just making these up from scratch. All right, so these numbers would not make sense in real life because the water would all have evaporated. But anyway, this shows us how to do the technical process. This is how to do the technical process of working out the change for the calorimeter. So the point was that you saw now how to use the answer from part A for part B. So you saw the basic method here, even though the numbers didn't make much sense. Let's see. Now, remember we had two different equations here. So what was the, so in this case, is the calorimeter absorbing or releasing heat?
In this case, just absorbing it.
Yeah, so would Q calorimeter be positive or negative?
Positive.
And that's what you plugged in. What would be the Q for the reaction? What's the Q for our reaction here? Is the reaction absorbing or releasing heat?
Q of the reaction is going to be releasing heat.
Because it's a combustion reaction, the heat is released. So what would Q for the reaction be?
Q for the reaction would be negative 23,851 kilojoules.
That's right. If you were going to use Q for the reaction, though, then you would use this equation. Remember, we have two different equations that you could use. You decided to use the first one, Q for the calorimeter. So you plugged in a positive number because the calorimeter is absorbing heat. If you were going to use this reaction, you would have plugged in a negative number, negative 23,851, but you would still get the same answer because the negative would cancel with the negative on the right-hand side. So you can use either of these two equations as long as you're careful to plug in the right Q. So in general, will Q for the reaction be positive or negative?
In general, Q for the reaction will be actually, negative.
When we're doing these types of combustion reactions that we do calorimetry on, and will Q for the calorimeter be positive or negative?
It'll be positive.
Because the calorimeter is absorbing that heat. So as long as you remember that, you can use either of these two equations. All right.
For part A, why wouldn't our answer be negative 23,000 joules? Because it's for a reaction, so I was thinking maybe the final answer should be negative.
Yeah, that's a little bit subtle. So if they'd asked you, what is the heat of the reaction? If they ask you for the heat of the reaction, and a good symbol for that would be Q reaction, then a good answer would be negative 23,851 kilojoules. But they didn't ask for heat of reaction, they asked what is the heat released. When you say released, that's already, the negative sign is, I don't know, it's hard to put into words, but it would be weird to say that the heat that's released is negative 23,000 kilojoules. So if they say the heat of reaction then you need to give a negative sign to show that the heat is being released. But if you just say the heat released is 23,851, then it doesn't make sense to put in the negative sign. Does that make any sense?
Yeah.
Okay. So that's a little bit of a subtle issue. If they say heat of reaction, if you say the heat of reaction is, you need a plus or a minus sign to show whether heat is being absorbed or released. But if you say the heat released is, then you don't need a negative sign because you already said that the heat was being released by saying the word released. All right, it's a little hard to put that into words, but that was a good point. Okay. I see what I did wrong. Okay. Okay, so let's try this problem.
Well, they're looking for TF. And we know that the heat of combustion But we need to figure out the heat of combustion released. So we can take 1645 kilojoules per mole, and then we have to multiply that by, let's see, first actually we'd have to take 0.8 grams of methanol, and then divide it by 12, 16 plus 4, 32 grams per 1 mole. And that gets 0.025.
How did you get that 32?
12 plus 16, plus 5, so 33.
Good.
0.024. Now we have that many moles of methanol combusted. So we take 0.024 and multiply it by 1645 kilojoules per mole. That gives us 40 kilojoules released. And then we can multiply that by 1,000. To get 40,000. And that would be Q of the calorimeter, so now we can take Q of the calorimeter is equal to specific heat times delta T, where Q is 40,000, and that is equal to 3 kilojoules per degree Celsius times TF minus 30, and 3 kilojoules times 1,000 is equal to 3,000 joules.
Let's back up for a second here. Why did you change this number into joules?
I'm sorry?
Why did you change this number into joules?
Because the usual units for heat capacity are in joules.
That's I guess maybe that's how we've done most of our earlier problems. But what we want is for all the units to be consistent. So are the constants in this problem mostly given in joules or kilojoules?
Kilojoules.
So actually, we'll make our life a lot easier if we just do the whole thing in kilojoules. So actually, let's erase this step. There's nothing wrong with what you're doing. You can still get the problem right. But you notice you're getting pretty big, unwieldy numbers. So instead of plugging in 40,000 for Q calorimeter, what are you going to plug in?
Just 40.
And then what do you plug in for C?
3.
Because that's in kilojoules. Then that way we have easier to use numbers. So the key is just to use units that are consistent with each other. So you have to use judgment to decide what's more convenient on each problem, kilojoules or joules. So it's good that you were thinking about the units, but I think this will be more convenient. Okay, so now what?
So now we can distribute, and then we get 40 is equal to 3 TF minus 90. So add 90. And then that's 130 is equal to 3TF. And I get the final temperature is equal to 43 degrees C.
Does that seem like a reasonable temperature?
Yes.
Yeah, that seems reasonable. Much more reasonable than what we got in the last example. So now I think I can see, what did I do wrong on the last? Oh, so what I did wrong in the last example is I added way too much octane. This would be way too much than you could actually test in a normal calorimeter, because it would release way too much energy. Notice here I was using a much more realistic mass, a much smaller mass. So if you're doing like a normal size calorimeter, you can only combust a small mass. Otherwise, you'll just end up vaporizing all your water. Okay, so so this came out more nicely. All right, so now we're starting to see a more systematic method for doing these problems. Where was I? Let's see. Okay, I just made up this number. That's not the real density. But if we make up this density number, try this problem.
Two milliliters of CH3COH density is how many moles? Okay, well, we have 3 milliliters CH3COOH. And then we can multiply it by 0.8 grams per 1 milliliter to get the milliliters to cancel. So that's 0.24 grams. .4 grams CH3COOH, and then that's 4, so 24 plus 32 plus 4 is equal to 60 grams, so divide that by 60 grams per 1 mole. That is equal to 0.4 moles CH3COOH.
What was your answer?
0.4 moles acetic acid.
Like this?
Yeah.
Okay. What did you get when you multiplied the 3 times the 0.8?
2.4.
And then you divided by 60?
Yeah.
And what did you get?
Oh, whoops, I read it wrong. 0.04.
Like this?
Yes.
Okay. Okay. Now, a good place to start here would be to write down the units, our target units. What are our target units?
Moles.
Of acetic acid. Okay, that was good. That was actually some good progress. This is a new problem that you and I have never done together. You and I have never done a problem like this before, but you were still able to figure it out with no help from me just by using unit analysis. So that's actually good progress, the way that you attacked that. You actually did this in 2 separate steps. In this case, my personal preference would be to do it in 1 step. I'm not quite sure why. So I just wrote it out in 1 step. You can see you can do this in 1 step. First, you cancel out the milliliters and transfer into grams, and then you can cancel out the grams and go into moles. So you used unit analysis to go from the units that you were given into the units that you wanted. You had a certain volume of the acetic acid solution, and you converted that into a certain number of moles of acetic acid. So that's a good example of how you can use unit analysis to do a new problem that you've never seen before. So that's good, the way you worked that out. Like I said, you could just do this in 1 step, but the way you did it is correct too. Okay, that's good. So what's the name of this concept?
Unit analysis.
Yeah, what's the name of this number here? What concept is this measuring?
Density.
Yeah, as it was given. So one thing that a lot of students don't realize is that densities can be used as conversion ratios. That was a good insight that you had on this problem. You and I haven't worked much with density, but the point is that density can be used as a conversion ratio. Pretty much any concept that has fractional units can be used as a conversion ratio. Any concept that has fractional units can be used as a conversion ratio. So that was a good insight, that you could use this as a conversion ratio, just like you can use molar mass as a conversion ratio. That was a good process. All right, so let's see. So again, I'm just going to make up a density. This probably is not the correct density, but I just made that up. Density. this number 2 I'm just making up. Okay, so let's try this.
Well, we'll first have to take 2 milliliters of ethanol and then multiply it by the density, 1.29, or sorry,
Let's start by
1.2
writing down a
grams.
symbol for what the question's asking us. What would be a good symbol for this? What this question's asking?
Oh, TF.
And what could you predict?
I'd say it'll increase.
So what do you predict about the final temperature?
It's going to be greater than 20 degrees Celsius.
Good. How do we know? Because we know that a combustion reaction is releasing heat. Okay, anyway, let's go back to here then. So what was this?
Oh, 2 milliliters of ethanol times the density, 1.2 grams. So 1.2 times 2, that's 2.4 grams of ethanol. And then we have to convert that to moles. So then we have 24 plus 16, 6 plus 6 is 46 grams per 1 mole. 2.4 divided by 46. So 0.0. So now it gives us 0.05 moles of ethanol combusted. We can take that number and then multiply it by the negative 2,500 kilojoules per mole. So that will give us negative 130 kilojoules released. Now we can take Q equals C delta T, where negative 130 is equal to C, which is 5.2.
Let's go back to this step. So this is the calculation that you did?
No, I multiplied that by 2,500.
Oh yeah, I got confused. You're right. You should be doing 2,500 kilojoules per mole, and then you would get, what did you get for that?
I got 130
kilojoules. Negative 130, I guess. Okay, that's right. Good.
Now, negative 130 is equal to 5.2 times TF minus 20. We can distribute. So negative 130 is equal to 5.2 TF minus.
So let's go through this together a little bit.
104.
So first of all, you need to write the general equation, like this, right? Now,
Yeah.
is this the equation you wrote down?
Yeah, but I said negative 130 is equal to 5.2 times TF minus 20.
So this is the Q of what?
Q of the...
Actually, let's go back to this. This is a Q. This is the Q of what?
The reaction.
Right. So what's the Q for the calorimeter?
So Q is equal to... Q of the calorimeter is equal to C delta T.
Right. What's the numerical value for the Q for the calorimeter? What number do we plug in for Q of the calorimeter?
We put positive 130.
So what number would you plug in here for Q of the calorimeter?
130.
Yeah, now maybe I was wrong. It sounded like you were plugging in negative 130.
Oh.
So that would definitely mess us up. So if you're thinking in terms of, if this is the equation for the calorimeter, you have to plug in the Q for the calorimeter. It's always the signs that are the peskiest here in chemistry. So since you're using this equation in terms of Q for the calorimeter, you have to plug in the positive number. So it's important here to distinguish between Q for the reaction and Q for the calorimeter. The reaction is releasing heat, so its Q is negative. That means that the apparatus is absorbing that heat, so its Q is positive. If you plug in a negative number, the answer won't come out right. We would get the wrong answer, so it's important to do that correctly. In fact, the answer might not even make any sense. All right, and what are you plugging in for capital C?
5.2.
Good. And what did you plug in for delta T?
TF minus 20.
Okay, good. Now what?
Now we can distribute, so we get 5.2 TF minus 104 is equal to 130. And then add 104 to both sides, we get 234. So 234 divided by 5.2 is equal to the final temperature, which is equal to 45 degrees Celsius.
Does that answer make sense? Does that answer match your prediction?
Yes.
Because we predicted the final temperature would be increasing, and this is increasing. Okay, well, I think in general you had a good process here for this problem. The one thing that was giving us trouble, though, was the signs. That's often a problem here. So now, I think in the previous problems, when I gave you the heat of combustion, I gave you the heat of combustion as a positive number, but maybe that was a mistake. Since combustion reactions are exothermic, maybe I should have been saying the heat of combustion was negative. So I think that's the way they're doing it in your sample problems. So here maybe I did it better. I gave you the heat of combustion as a negative number to show it's exothermic. So the important thing here is to carefully distinguish between Q reaction and Q calorimeter. That's the thing to highlight in your notes. Don't confuse Q reaction and Q calorimeter. If you're using this equation, you have to plug in Q calorimeter, which is the negative of Q reaction. Remember, we spent a long time earlier in this session today seeing the relationship between Q calorimeter and Q reaction, and we saw that one was the negative of the other. And this is the reason why we had to go over that in order to deal with this. There's another way you could have done this. You could have used this equation for Q reaction. If you use this equation, then you could just plug in the negative number for Q reaction. But I think the way you're doing it probably is more intuitive. You're using this equation. I think that's probably more intuitive because this equation looks more like the equation that we were using before. So maybe I'll erase this and we'll just focus on Q calorimeter. Let's try this problem.
The following substance undergoes complete combustion in a bomb calorimeter. The bomb calorimeter assembly, including the water, has a heat capacity of 4.88 kilojoules per degree Celsius. In each case, what is the final water temperature if the initial water temperature is 24.62 degrees Celsius? A. 0.5187 grams of cyclohexanol. Heat of combustion is equal to that. Well, first we have to convert the grams to moles, so 0.518 grams.
Let me interrupt you. First of all, we should write down a symbol for the question. What's a good symbol for what this question's asking?
Oh, TF.
And then we should get a prediction.
I'm going to predict that it's going to be greater than 24.62 degrees Celsius.
Why?
Because it's a combustion reaction.
That's right. So okay, good. All right, so then we can go back to our work here.
So we have 0.5187 grams, and we divide it by 100 grams per 1 mole. 12 times 6 plus 16 plus 12, 100, so 0.5178. 5187 divided by 100 is equal to 0.005187 moles of cyclohexanol. Now you can multiply that by the heat of combustion, which is a negative 3727 kilojoules per 1 mole. And that is equal to negative 19 kilojoules. Of heat released. And since this is Q for the reaction, we can use either Q cal or Q reaction. So Q calorimeter is equal to C delta T, where Q calorimeter is equal to 19, and that is equal to 4.881 times TF minus 24.62. Now we can distribute. Minus 120. So add 120 to both sides. And that'll give us 139 is equal to 4.881 TF. So that was 4.881. And I get TF is equal to 28 degrees Celsius, which matches my prediction.
That's a good thing to check. So let's see. I didn't round off very much on my calculator, so I got 28.6 degrees Celsius. I guess this handout, they didn't give us the answers, but I think we got that right. All right, so it should be somewhere around 28 degrees, depending on how you round it off. Okay, good. That was a good process. All right, that didn't give you much trouble, but we've put together a whole bunch of steps here. First, we had to translate from grams to moles. How did you know that you needed to translate into moles? Because the heat of combustion was in terms of moles. And notice in this case, all the constants are in kilojoules, not joules. So we may as well just use kilojoules for everything. So here we have negative 19.33. What's the symbol for this? What symbol is equal to negative 19.33 kilojoules?
That's Q of the reaction.
That's right. But you were going to use the equation for Q calorimeter, so you had to say to yourself that if Q reaction is negative, then Q for the calorimeter is positive 19. So we plugged in the positive number here. Good. And notice that they said this was a bomb calorimeter. But remember, all that means is that it's a sealed vessel with constant volume. It doesn't really change how we're going to solve the problem. Okay, that's good progress on that. So now let's do part B. Let's do part B.
.75 milliliters of ethyl acetate. Okay. So they give us 1.75 milliliters. And I guess they are also looking for the final temperature, so TF. And since it's a combustion, then it's going to be greater than 24.62 degrees Celsius. So 1.75 times 0.901 is equal to 1.57 grams of ethyl acetate. And then you can divide that by 48 plus 32 plus 8, 88 grams per 1 mole. And that's equal to 0.01, like 0.02 grams or moles combusted. So we take 0.02 and then we can multiply it by heat of combustion, negative 2246 kilojoules per mole. And that's equal to negative 40 kilojoules of heat released. Now we can use Q calorie, and that's 40 is equal to 4.881 times TF minus 24.62. You can distribute, and we get 40 is equal to 4.881 TF minus 120 So we can add 120. And that's 160 is equal to 4.881 TF. And that is equal to 33 degrees Celsius, which matches my prediction.
Okay, you're working a lot faster than I did. So let's see, you ended up here with... So is what I'm writing down, does that match what you had?
Yes. I'm sorry, where'd you get the 81.99 from?
Maybe I made a mistake. So let's see here. You had 0.002 moles. So what number did you write down here?
I did 0.002 times 2246.
You're right, and I'm wrong. I was looking at the wrong problem. I was taking the number from the wrong problem, so I got confused. This should be 2246.022 times 2246. So what number did you get for this? What was the number you got here? Are you working that out again, or? Hello?
Yes.
Okay. Do you have that written down?
Yeah.
All right. So what number did you get here?
That one was I got negative 40.
I'm still getting something different. You said negative 40?
I got oh sorry, 0.02 times 2246. 0.02 times 2246. Yeah, I got 43.
Okay, it really depends on how you round off. Let's see, I rounded off a little less than you, I think, so I got 49 here. So put that in.
Steven, are you available tomorrow?
Yeah, we can schedule something after we finish this. All right, so so now would that give you this equation?
Now you would use Q-cal is equal to C delta T, where 43 is equal to 4.881 times TF minus TI. And you can distribute, and you get 4.881 TF minus 120 is equal to 43.
Okay, good. And what did you get as your final answer?
33 degrees Celsius.
All right, yeah. I rounded off a little different, so I got a slightly different answer. But it looks like we're on the same page. Okay, good. All right, that's some good progress on this. There was actually a lot of complications here. You had to change from the volume into grams. You had to use the density as a conversion ratio, so we went over how to do that. Then you changed that into moles so that it would match up with the heat of combustion, and then you plugged into here. So this negative 49, what symbol is equal to negative 49 kilojoules?
That's Q of the reaction.
Right. But for this equation, we need Q for the calorimeter, which was positive 49. So that didn't give you trouble. And then that matched your prediction. Okay, good. What time would you like to schedule for tomorrow?
Are you available at 11?
11 Pacific? Yes.
Okay, that'll be fine.
Okay, so that's tomorrow, Sunday, October 28th, 11 to 1 Pacific. Did you get a chance to go through those other problems in the first 4 handouts here?
Not yet, no.
Okay, so that would be a good thing to do. Practice makes perfect. We spend a lot of time on that, so you want to make sure you'll get those problems right if you see them on the test. So the first 4 pages of those files that you sent me, all those temperature and phase change, you should be able to do all those on your own. And you have answers for those. So those would be good ones to go back and try again and do. Also, it would still be helpful if you could send me test 1 from your course. Is that something that's available?
Yes. I just haven't had a chance to
okay, yeah, that's
make
fine.
copies of it and get it in the email.
Okay, so when that's possible, that would be helpful so that I can see how hard the questions are that your instructor is giving you, so we can do something similar together. Okay, and obviously you want to try to redo the questions that we just did together so that we can move on to the harder problems tomorrow. Okay, thanks.
Okay, thank you.
Bye.